Looking at the next element of the fifth group, which is phosphorus. Phosphorus is still non-metal, sitting just below nitrogen, but it's much larger, as you've seen before. So you may have more neighbors around phosphorus atoms. Phosphorus can make P2 molecule in gaseous phase, but that's rather unusual. So more common is P4 tetrahedral molecule, which makes single bonds instead of triple bond between phosphorus atoms. Distance between phosphorus atoms is too large for double and triple bond to be stable. This molecule can make a solid, which we may name white phosphorus. In fact, even small impurities in white phosphorus make it slightly yellowish. So there is common name yellow phosphor for impure white phosphorus. White phosphorus easily reacts with air, even on cold, need to be protected from air. So it's very reactive in general. When it reacts on dark, it emits some chemiluminescent light, and that's where the name phosphorus coming from. You have some light coming. Far less reactive is so-called red phosphorus, just two different samples. There is also one more, black. The difference between these all compounds are polymeric. In black you have layers of tetrahedral phosphorus atoms, making three-dimensional structure. Synthesis of phosphorus is a large-scale chemical process. Starting material usually is calcium phosphate, which is apatite. That reacts with carbon monoxide coming from burning of coal, or actually not coal, but coke. We already talked what is that. Then decomposition, you are making calcium oxide solid, CO2 gas, and P4 at this temperature it will be gas. Now to shift equilibrium we need to bound calcium oxide and CO2. We do that by addition of silicate, SiO2, as a sand. So calcium oxide reacts with acidic SiO2 to make salt calcium silicate, and CO2 reacts with carbon coke to make carbon monoxide, which recycles in this process. Now it's a very complicated process. As a result, you're taking a large amount of calcium phosphate, actually that's rock, lots of sand, lots of coke, and lots of electrical energy to heat all this. You're receiving white phosphorus, you're receiving calcium silicate, which has usage. You're also receiving from iron admixture in apatite a large amount of iron phosphides that have metallurgical use, and you have filtered dust, which can be source of rare earth elements and other very interesting chemical compounds. That's very nice inorganic source material. You also have flue gas that can be used for energy production. So only when you use all these components, not only white phosphorus, but all of them, and possibly separate plenty of rare elements that were in your apatite as admixture, all these and only these makes the economical process feasible. Phosphorus makes phosphides with metals like nitrides. You have phosphides, which in turn can react with water to make pH3 gas, similar to ammonia gas, and calcium hydroxide. Now the size of lone pair is larger. The distances between hydrogen and element are larger in case of phosphorus, so the angle is smaller here. The same trend continues with arsenic and antimony. You have larger and larger element hydrogen distances, so they can come closer. Phosphorus easily reacts with oxygen to make P2O5, or more precise, P4 or 10 solid, because this is molecular solid, tetrahedral molecule like that, with different phosphorus-oxygen bonds. So these are more double, these are more single, longer bonds. Structure can be drawn this way. That's white powder, very hygroscopic, very easily react with water to make phosphoric acid. You also can make P2O3, or more precisely P4O6 oxide. Here oxidation number is 5, here it's 3 plus. Again, it can react with water to make appropriate acid. So phosphoric acid. Phosphoric acid can be directly made from apatite without going through phosphorus. So calcium phosphate reacts with concentrated sulfuric acid to make H3PO4, calcium sulfate precipitates, and you have water. Now, while purity of phosphoric acid received by this process is very low. Phosphoric acid, when it's pure, it's liquid, very viscous, and in water it's a weak acid, but when you have its anhydrous solution, it can behave as a reasonably strong one. When you heat it, it releases some part of water, giving polymeric structures. So because it's heating, the old name would be pyrophosphorus acid instead of diphosphate. You can continue to triphosphate like this. If you dehydrate this compound, you receive something that will resemble nitric acid. You remember it's HNO3, but HNO3 is a single molecule. HPO3 is not HPO3. It's a polymer with 3 phosphorus atoms and 3 hydrogens and 9 oxygen atoms. So it's actually H3P3O9. Anyways, simplified formula will be HPO3. And all phosphorus atoms will be tetrahedral. As you can see, a tetrahedral environment is very common for phosphorus, like it's common for its neighbor silicon. Phosphorus makes halogenides like nitrogen has, but the most stable are of oxidation number 5. PCl5 molecule will have usual trigonal symmetry, but when you make a solid, it contains positive PCl4 ions and negative PCl6 minus ions. Very common situation with phosphorus. With fluorine, you can make PF6 octahedral ion, which is unusual for oxygen, but it's common for smaller fluorine. It's possible. The same compound we already have seen, SbF6 from the same group. So SbF5 reacts with hydrofluoric acid to make superacid like that. Very similar situation with phosphorus.